Hi everyone, welcome to part 3 on our video lecture for section 3.3, dealing with the derivatives of polynomials and exponential functions. In the previous two recordings, we discussed a bunch of different formulas that can help us find the derivative quite easily, as I've been referring to them as the shortcut rules. In this video, we'll take a look at a couple more examples and define a normal line. Alright, so let's go ahead and get started here with example 5, where we're being asked to find the x values on the curve y equals to x to the fourth minus 6x squared plus 4, where the tangent line is horizontal. Alright, so how do we proceed here? How do we know which x values will have a tangent line that is horizontal? Well, let me give you guys an example of a graph here to get the point across. So let's say I give you a graph like this. Now we can spot where we're going to have horizontal tangent lines. I take a look at a point here, and I get to see here that yes, a tangent line at this point here would be horizontal, as well as right here near the bottom. It's like, okay, so at those two places, my tangent lines are horizontal. Now, if I were to ask you for the slope, you would tell me that the slopes at this line is 0. But remember though, the slope for a tangent line is the same thing as a derivative. So what we're really looking for is, hey, where is the derivative equal to 0? And that's exactly what we're going to do for this problem. We're going to go ahead and find a derivative and then set it equal to 0 to figure out, hey, where are the tangent lines horizontal? Alright, so let's get to it. Welcome back. For this derivative, I got a 4x cubed minus 12x. Okay, so we got the derivative. Now the second step is to set our derivative to 0. Okay, so how can we solve this equation? Well, hopefully you notice that there is a GCF. I can factor out a 4x, and what are we left with? Well, we should be left with an x squared minus 3 equals 0. Now, using the zero product property, we're going to go ahead and obtain a 4x equal to 0 and an x squared minus 3 equal to 0. So let's go ahead and solve both of these equations. So for the first one, where we have 4x equal to 0, we can clearly see that x has to be 0. What about for the next equation, where we have the quadratic? Well, what I'm going to do here is I'm going to go ahead and isolate this square. So we're going to have x squared is equal to 3. Take the square root of both sides. Not forgetting about the plus or minus though. We're going to get then that x is equals to a square root of 3, or x is equals to a negative square root of 3. And that's it. We're done. What we just found here are the x-coordinates for the places in the graph where the tangent line is horizontal. Excellent. And again, I'll emphasize it here. For these 6 values, the slope of the tangent line is 0. Okay, perfect. Now, we talked about tangent lines, so I want to go ahead and talk about a new type of line known as normal lines. Alright, so what is a normal line? Well, a normal line is defined as the line that is perpendicular to the tangent line at the point of tangency. Now, you might remember hearing the word perpendicular in some of your math courses. Perpendicular lines are just lines that are forming a 90-degree angle, and I'll put it here. Now, because the slopes of perpendicular lines, neither of which are vertical, are negative reciprocals of one another, then the slope of the number line to the graph of f of x is simply negative 1 over f prime of x. Because again, we already will know what is the slope of the tangent line. So the slope of the normal line, it's its negative reciprocal. And let me give you guys here a quick sketch. So let's say that we're given this function here, something like this. Alright, so if we're going to go ahead and find out, let's say, the tangent line at x1, it's like, okay, well, we get to see here, okay, this is our tangent line at x equals to 1, and let's give this one here a slope of, I don't know, 2. Well, the line perpendicular to it will be this line right here. Oops, missed it. Something like this. There we go, forming a 90-degree angle. And this one here is going to have a slope of the negative reciprocal of 2 is going to be a negative 1 over 2. So that's the idea here. Okay, so now let's put this concept into practice with example 6. let's see if we can go ahead and find the equation for the tangent line and the normal line to the curve y equals to x cubed plus 2x minus 3 at x equals to 1. Okay, since we're looking for the equation for the tangent line, that means that we need to find out what is the slope of the tangent line. In other words, hey, what is going to be the derivative at x equals to 1? So let's go ahead and find this derivative. All right, so our derivative, y prime, is going to be equals to, all right, so what is the derivative of x cubed? Well, the derivative for x cubed is just going to be 3x squared. Okay, so we're going to get a 3x squared plus, okay, now what is the derivative of 2x? Well, the derivative of 2x is just a 2, so there we go. Now we have plus 2 plus, now what is the derivative of a negative 3? Well, the derivative of a negative 3 is just going to be 0. So there we go. Here we have our derivative. Now, I'm going to go ahead and change the notation here to give you guys more exposure to different types of notation. And I'm going to go ahead and call this one here dy dx. All right, so this is the derivative function, which tells us the slope of the tangent line at any x. But right now, we're looking specifically for the slope of the tangent line at x equals to 1. So let's go ahead and evaluate our derivative at x equals to 1. So I'll go ahead and use the notation that we discussed last week, and I'm going to go ahead and write down dy dx with a vertical var to let us know that we will be evaluating the derivative at a given x, in this case, at x equals to 1. All right, so plugging 1 into our derivative function, we're going to get a 3 times 1 squared plus 2. Well, let's see, 3 times 1 squared, that's just 3, plus 2 is going to give us here a 5. All right, so it looks like at x equals to 1, the slope of the tangent line here is 5. Excellent. Now let's go ahead and get the equation for the tangent line. All right, so for the equation of the tangent line, hopefully by now you've practiced a couple of examples here. So we're going to get the notation that I talked about here in class was f of x minus f of x1 is equals to the slope of the tangent line, which is the derivative evaluated at x1 times x minus x1. All right, so we already know that for this problem, the x1 here is 1. Okay, but what about the f of x1? All right, so what is f of x1? So if we know that the original function was x cubed plus 2x minus 3, let's see, what is f of 1? If we plug in 1 here, let's see, we would be getting a 1 cubed. So 1 plus 2 times 1 is 2, so 1 plus 2 is 3. Minus 3 gives us a 0. Okay, so it looks like f of x1 is just going to be a 0. Okay, now what about the derivative? Well, we already said that the derivative at x equals to 1 was equals to a 5. All right, so we pretty much have everything ready here. So we have our equation, f of x is going to be equals to 5 times x minus 1, which is just going to give us then a 5x minus 5. Okay, now what about the equation for the normal line? Well, we pretty much have almost everything that we need. We're still going to be using the equation for a line, f of x minus f of x1, which we already know, is equals to the slope, which we'll find here in a second, times x minus x1. Okay, now the only thing that is going to be different here is the slope. Now remember that since we're dealing with perpendicular lines, the slope here, I'll put here m perpendicular, is simply going to be negative 1 over the slope of the tangent line evaluated at our point of interest, which is a 1. So our slope here is just going to be negative 1 over f prime of 1, which is going to be negative 1 over 5. That's the only thing that's different. So for our formula then, we're going to get f of x minus f of x1, we said it was a 0, is equals to a negative 1/5 times x minus 1, which is going to give us then the equation for the normal line is going to be equals to f of x is negative 1/5 x plus 1/5. And there we go. We got our equation for our normal line and our equation for the tangent line. Now, I want you to see all of these lines coming together on Desmos. So let's take a look. So going to Desmos here, we can take a look at the original function, x cubed plus 2x minus 3. Okay, next I'm going to go ahead and graph the equation for the tangent line at x equals to 1. And in fact, let me mark the point here, x equals to 1. It was at 1, 0. Perfect. Now, let's take a look at our equation for the tangent line. There we go. Here is our tangent line. Now, what about the normal line? And again, remember, it's the normal line at x equals to 1, but that is the line that is perpendicular to the tangent line. So if I go ahead and graph it here, there we go. Now we have our normal line, and it does seem to be forming a 90-degree angle or forming a cross. And there we go. Now you'll see a lot more applications for tangent lines and normal line in other Review Math courses, but right now we're learning about the concept here. Alrighty guys, so this is where we're going to be stopping here. I was going to work on another problem, but I figure I'd save that problem for class. Alrighty, so this is it. I'll see you guys later. Have a good one.